In your last video, you learned how to calculate the number of combinations of something happening. And we looked at the formula, we were able to calculate it, and hopefully you were able to make some sort of connection between that goofy Pascal triangle and the number of combinations. If you weren't able to do that, I'm about to show you in this. And then we're going to see how it all ties together as it relates to binomial probability. So let's just take a look back at the last problem that we were looking at about leaving a tip when you order takeout. So we had a hypothetical situation where there's a 35% chance that any person leaves a tip on a takeout order, and we had 5 people picking up their orders. And you were asked to find 2 different probabilities. One, what's the chance that the first 2 leave a tip and then the next 3 do not? And that one was simple enough. We had 5 slots, and we had the first 2 leaving a tip and the last 3 do not. And to calculate that, we just took 35% times 35% times 65%, 65%, 65%. We multiplied them all together, and we got 0.0336, I believe. So about a 3% chance of that sequence of events happening. And that's just independent events happening, and you just multiply them. That one was simple enough, but then we moved to one that was a little bit more difficult. And the question was, what's the probability that 2 people leave a tip and 3 do not? Now I'm not specifying the order. I'm just saying any 2 of them will leave a tip. And hopefully what you saw was there were 10 different ways that we could have 2 people leave a tip. And we ended up multiplying that by 0.35 squared times 0.65 cubed. And you see that over here. This is the 0.35 squared. This is the 0.65 cubed. And this sequence of events could happen in 10 different ways. That's why we had that 10 there. Now you might be wondering, how did you find that 10 without having to draw it all out? Because once you get to bigger numbers, you don't want to have to draw all these out. So I'm going to show you. Here's Pascal's triangle. Almost there. We'll go to this last row here. All right. Hopefully you made the connection at the very, very end of that last assignment. And I'm going to show you how this row gets filled out. This one here, notice how it's row number 5. Technically it starts in row 0. So here's row 0, here's row 1, here's row 2, here's row 3, here's row 4. This is row number 5. And you see that because it has a 5 in the second spot. But to get that first number in row 5, it's just 5 choose 0. And to get the second number in row 5, it's just 5 choose 1. To get this next one, it's 5 choose 2. The next one is 5 choose 3. This one would be 5 choose 4. And this last one, I don't have room to draw it, but it's 5 choose 5. And so what's happening in this one is we have 5 people going out for takeout, and we're choosing 2 of them that will leave a tip. 5 choose 2 is this number right here, which told me that there were 10 different combinations of that pattern happening. So that's how I ended up getting 10, and then we multiplied it by the corresponding probabilities. So that's essentially what we're going to be doing today when we're calculating binomial probability. Let's start by giving you the formula. What is the formula that can be used to calculate binomial probability? You've got x is approximately binomial. This is just formal notation stuff. N stands for the number of trials. P stands for the probability of success, meaning like the probability of something happening. Success usually gets like a good connotation. It's not always a good thing. And that's going to be equal to the probability that x equals some number r equals, I'm going to go down here, it's n choose r times p to the r times 1 minus p to the n minus r. I'm going to get rid of some of this for you. So this is This is essentially the formula that you're going to need for this. N choose r times p to the r times 1 minus p to the n minus r. I know that's a bunch of letters in there. We're going to look at how those letters actually make sense. So it's basically just the probability of something happening or not happening, and then plug in some numbers. When is it appropriate to use this formula? It's appropriate. It's named binomial, bi meaning two. There's only two options. Something either happens or it doesn't. So it's when something happens or doesn't. So there's only two options. It's either going to happen or it's not going to happen. That's binomial. And lastly, you're performing multiple trials. In the example that we had up at the top, they either left a tip or they did not leave a tip. And we have 5 people, multiple trials. Let's take a look at the first example. When going bowling, Leah has a 9% chance of getting a strike. That's when you knock down all 10 pins. Leah's not a very good bowler. And she's going to bowl for 10 frames. So that's a standard length of a bowling match. What's the probability that she gets exactly 1 strike? So to find this probability, first off, how many trials are there? She has 10 tries to get these strikes. So there's going to be 10 trials. So it's a binomial probability where it is 10 trials and the probability of something happening is 0.09. So that's just kind of some notation stuff. You don't really need to know that. To calculate this probability, we are going to do 10 choose 1 because there's 10 trials and she's going to get exactly 1 strike times the probability of success, so 0.09, and you're going to raise that to the first power. She's going to get 1 strike. And then it's going to be times 0.91 to the 9th power. So I want to break this down and make sure we understand what's happening. She's bowling 10 frames. This 0.09 to the first represents she gets 1 strike. That strike happens 1 time. This 0.91 to the 9th power means she's not getting a strike. That was 91% of the time, 9 different times. And this 10 choose 1 shows you how many different ways she could get that 1 strike. It could happen on the first frame, or the second frame, or the third frame, or the 4th frame, 5th frame, 6th frame, 7th frame, 8th frame, 9th frame, or the 10th frame. There are 10 different ways that she could get exactly 1 strike. And we're going to multiply it by 0.09 to the first times 0.91 to the 9th. And if you do that calculation, you end up with a 0.385 probability. So she has a 38.5% chance of getting exactly 1 strike when she goes bowling. Let's find the probability of getting exactly 2 strikes. So this would be a little better for her. She bowls 2 strikes. We are now going to do 10 choose 2. So that will show us how many different ways could she get those 2 strikes. And it's going to be times 0.09 to the 2nd power. So this is the probability of her getting a strike, and she has to get 2 strikes now. And then it's times 0.91 to the 8th power. So she's not getting a strike 91%, and that has to happen 8 times. And to calculate this, we can find 10 choose 2. You can use the skills that you had in the last video, or I'll show you later on how you can just use a calculator for it. But this becomes 45 times 0.09 squared times 0.91 to the 8th. And if you type all of that in, you get 0.171. There's a 17% chance that she'll have a game of bowling and get exactly 2 strikes. And next one, what's the probability that she gets no strikes? This wouldn't be a very fun game. she's going to bowl 10 frames and get no strikes this time, times 0.09 to the 0 power times 0.91 to the 10th power. What this means is she gets no strikes, and she gets 10 of these not strikes. Anything choose 0, 10 choose 0 is just 1. So it's 1 times 0.09 to the 0 times 0.91 to the 10th. If you multiply all of that out, it ends up becoming 0.389. She has about a 39% chance of getting no strikes. And here's one phrase that we're going to get used to very quickly. What's the probability she gets at least one strike? Let's just say all she wants is to get one strike. She doesn't care if it's 1 or 2 or 3. She just wants one. She wants to know what that feels like. So she could, hypothetically, go bowling, and she could get 0 strikes. That would be a bummer. Or she could get 1 or 2 or 3 or 4, or she could, if she was really amazing, get all 10 strikes. The phrase at least 1 just means 1 or more. So she could get 1 or 2 or 3 or 4 or all the way up to 10. And you don't want to calculate all of these probabilities individually. It's much easier to just calculate this one and subtract from 100% or subtract from 1. So we already found that the probability of her getting no strikes was 0.389. And what that means is the probability of every other result, at least 1, would be 1 minus 0.389. And that gives us 0.611. So she has a 61% chance of getting at least 1 strike. She might get 1 strike, she might get 2, she might get all 10, but there's a 61% chance of that happening. And on your own, go ahead and try the next one. You have someone taking the ACT and there's 4 questions left, time is running out, and calculate the probability of getting 0, 1, 2, 3, or 4 answers correct. So go ahead and pause the video and see how you do there. If you have done it correctly, you should hopefully find that, I'll just give you one of the answers, the chances of you getting 3 out of 4 questions correct by just randomly guessing is 0.0256. There's only about a 2.5% chance of getting 3 out of 4. The chances of 4 out of 4 is even smaller. All right, last example. A fair coin has a 50% chance of landing on heads and 50% chance landing on tails. Suppose this fair coin is flipped 100 times. What's the probability that it will be on heads exactly 50 times? So it's a binomial probability because it's either going to be on heads or it's not. And we're doing 100 trials. So we're going to do 100 and we're choosing, it has to land on heads exactly 50 times. And then the probability of success in this case is 50%. And that has to happen 50 times. And the probability of not success is also 50. And that has to happen 50 times. Now, you probably don't have this number memorized from Pascal's triangle. That's okay. You can just go onto Desmos and you can find something called NCR. So on Desmos, find NCR, and then you're going to type in 100, 50, and it's going to give you a number like something times 10 to the 28th power, something obscenely big like that. That's fine. Just multiply it by 0.50 to the 50th power times 0.50 to the 50th power. And if you've done everything correct, it shows you the probability of getting heads exactly 50 times is going to be 0.0796. It's about an 8% chance. And the reason it's so small is because you're flipping it 100 times. The chances of getting exactly 50 heads, probably not super high. It's going to happen 8%. It'll probably show up around 50% of the time, but maybe not exactly 50. Go ahead and look at our top free throw shooter in basketball, Sam Gray. Look at him and see how he's going to do on that last problem. Thanks for watching, and I'll see you in the next one.